So, in the last class we for the interfacial heat and mass transfer we included the effect of surface tension and the disjoining pressure, and we found out the equations for continuity, momentum as well as the energy. Okay. In this class we are going to do the species balance, okay, before we move on to specialized topics. Now, in the species balance, unlike temperature, see temperature is continuous across an interface, right. Temperature is continuous, right, across the phases or across the interface, correct, right. But species or concentrations are basically discontinuous, right. Okay. So, okay. So, a general interface, if we consider a general interface between two phases, say phase K and phase J, right. Okay. And there is a mass flux, and in phase this is phase K and phase J. Now, the species that we are considering is I. Okay. So, there is a migration of species I or mass flux of species I between these two phases, right. Okay. So, K and J are not the species, these are the two phases. Okay. I is basically the species. Okay. Now, the total species mass flux, which is basically m dot I, okay, is basically it will be given as, and we will come across each and every one of them in details. Okay. And we will see what each of these terms exactly means. G I Okay. Now, this V k I, what you see over here is basically nothing but the velocity of species I, okay, in phase K, right. Okay. Similarly, this J I means the velocity of species I in phase J, right. Okay. It is like K, here it was one phase, this is the other phase. Okay. So, similarly over here you have basically two velocities that we have defined. Okay. Now, these velocities are further defined like this: rho k I V k I equal to j k I plus, got it. Okay. On the other hand, this you guys already know from your previous lectures. Got it. Okay. So, this is the velocity that has got a diffusion component, obviously. Okay. That is a diffusive flux, as you know, J is always the diffusive flux, right. So, the velocity of species I in phase K is represented in this particular fashion. Okay. Now, if you substitute these relationships, okay, back in the main governing equation, which is over there, okay, you get your m dot I double prime j k I dot n omega k I rho k v k minus v I is equal to j I, sorry, got it. Okay. So, that is now the species flux of the ith species. Remember always this is for the ith species that we have determined this flux term. Okay. Now, the overall mass conservation mass conservation at interface. This we already did in the last class, if you recall, was basically this, right. Right. This we already did in the last class itself, right. Okay. And based on this, your m dot I double prime now can be written as j k I, this is the diffusion term, plus omega k I m dot double prime, right, okay, is equal to j I dot n plus omega j I m dot double prime, right. Okay. So, you can understand that there is a diffusive component, there is a bulk component, correct. So, this is basically nothing but the diffusive component and this is more like the bulk component, right. Okay. Because if you look at this carefully from the previous equations, how we have actually written it is that if you look at this particular term, say for example here, this is nothing but the diffusion. This is the diffusion of species I through the phase k, okay, or through the phase j, correct. Okay. While on the other hand, this is nothing but the bulk velocity with which phase k is actually moving or phase j is actually moving, and as it is moving, it is carrying with it the mass fraction, okay, of whatever that species I is, right. Okay. So, it basically has got two components, bulk and the diffusion, right. So, that should be kind of clear to everyone. So, this is always the case. So, you have a diffusion of species and then you have a bulk of bulk movement, right. Okay. So, diffusion happens because of the diffusion coefficient, right, okay, and bulk happens because there is a bulk migration, okay, of one fluid into another, okay. And as you know, m dot double prime is equal to summation of m dot I double prime I to whatever n that you have, got it, okay. So, if the species flux is not specified, okay, the total mass flux will be okay, got it. Now, for a binary mixture, this diffusion flux J, okay, you know how to represent it for any particular mixture, okay. This is basically represented as something like a rho k d k 1 2 being the two components. This is basically nothing but the concentration gradients, if you look at it with this, okay. So, this is a very standard Fickian diffusion kind of a model, right, where this is the diffusion term and this is the concentration gradient, right. So, you can understand in one case this component was transported by the bulk movement, right. This is actually transported by the concentration gradient. So, this term is very much like your heat conduction kind of term, your Fourier's heat conduction. There is a concentration gradient, instead of d there you have k, right, and so there is a transfer of heat. Here instead of transfer of heat you have a transfer of mass, right, you have a transfer of species in this particular case. Okay. Now, the binary mixture can be in the presence of any of the phases. So, for example, here we wrote it in terms of some arbitrary phase, okay. It can also have it in terms of say liquid solid, solid liquid, then liquid gas. It can be with respect to any two combination of phases, right. Okay. So, it does not necessarily mean, so it is basically whichever phase it is present in, it is the diffusion in that particular phase, right. Okay. Say for example, you take the example of say a droplet, because droplet is something that we will cover immediately after in a short while. So, the droplet, say it's a binary droplet, let us assume for the time being it is a binary droplet. Okay. By binary it means let us say water and ethanol is actually present in this particular droplet, water mixed with ethanol, right, and this droplet is actually evaporating. This is the phase boundary, right. So, this is the liquid phase, this is the gas phase, correct. And what happens in the gas phase, both water and ethanol actually evaporates and gets mixed in the gas phase, right. So, the diffusion of water in ethanol in the liquid phase, when we are talking about this binary diffusivity, right, when we are talking about this, right, that coefficient, that d will be very different from the d that you have here, got it. So, the evaporation of water vapor in air, right, is very different from or the diffusion of water vapor in air is very different from the diffusion of liquid water in a water ethanol mixture, got it. Okay. So, liquid water, okay, say this water liquid, okay, is actually diffusing in a water plus ethanol mixture, right. Okay. So, it has got a certain value of diffusivity. Okay. On the other hand, water vapor in the vapor phase is diffusing, okay, say in air plus water vapor plus ethanol vapor, right. Okay. So, it is diffusing in all three of these. Okay. So, the diffusion coefficient this d and this d are very different, they are not equal to each other. Okay. That is what we mean, right. So, that you can easily imagine that in the gas the diffusion is pretty fast, whereas in the liquid the diffusion will be very slow, got it. Okay. So, but the idea was to give that it happens, mass transfer or species transport across the interface happens principally because of diffusion and this, right, individual diffusion and the mass transport that is happening, okay, between the two phases. Okay. So, this actually governs the evaporation. From here you can imagine things like evaporation, condensation and things like that, right. Okay. So, now let us look at this example that we have over here. Okay. So, this example can be of various types, but let us look at one significant one. Okay. So, here is the example. Let us take a liquid and a gas, okay, and the interface is flat. Okay. So, let us not talk about curvature and any other things, the depression of vapor pressure and stuff like that. Okay. So, the liquid, so the species here is XA, right, A is the name of the species, A is the species that is present both in the liquid phase as well as in the gas phase, got it. So, if we look at this particular thing in details, that there is a liquid phase and then there is a gas phase that are present. Okay. What is happening, what we are trying to do, so this is not a pure liquid, this is not a pure gas, right. Okay. So, there is this liquid has got several species, one of the species is A. Okay. So, A, when this A, the fraction of A inside this particular species is denoted as XA, XAL when it is present in the liquid phase, and when it is present in the gas phase it is denoted as XAG, right. Okay. So, this is basically the mass fraction, okay, of the species A in both the phases. Okay. This is direct corollary of the example that we just now saw. Okay. Now, on the other hand, this particular figure, this is a pure evaporation problem, right. This is how things evaporate. You have a saucer filled with water, this is how it actually evaporates, right. On the other hand, you have this solid to gas interface also, sublimation, naphthalene if you have seen. Okay. So, that is a solid gas media or two phases separated by a sharp interface. This is a liquid gas media separated by a sharp interface. Okay. So, evaporation and sublimations are typical examples of mass transfer, got it, two cases of mass transfer. Now, in case 1, if you look at, this is 1, if you look at case 1, okay, it is a pure liquid or a pure solid which is actually evaporating or sublimating, okay, into the gaseous mixture, okay, and it is purely controlled by the species gradient in the gas phase, right. Because why it is flat, that is because there are no other species present, right. There is no other species, the value has to be equal to 1, if it is a pure liquid, say we are evaporating pure water, this is pure water and that is pure that is the atmospheric air, right. So, in the liquid phase you are not going to have any gradient with respect to the water, right, because it is only pure water, it will be always 1, right, no matter what you do it will be always 1, right. So, here in but on the gas phase it need not be 1 because water vapor is going into air, right. So, air basically has got oxygen, nitrogen and all these things, right. So, water vapor is only a very small fraction of the air, right. So, once it evaporates you can see that you develop a gradient, okay, a species gradient in the gas phase, okay, but you do not develop a species gradient in the liquid phase, got it, in both the cases, got it. Okay. So, the concentration gradient also exists in the liquid in the case of 2, however, in case 2 that means it is not a pure liquid anymore, like the example that I gave, it may be water mixed with ethanol, water mixed with something else, right. Okay, it is not pure, okay. Therefore, concentration gradients will also exist in the liquid and the solid phase also, here and here you are going to have that concentration gradient, right. Why there will be a concentration dip, can you explain that? That is because, okay, it is basically supplying, right, the liquid is actually evaporating or that species is actually evaporating and going into the gas phase, right. So, if it is water, water is getting converted to water vapor. Since it is getting converted to water vapor, okay, there has to be a slope near the interface, right, otherwise how would it match the flux, right. This particular gradient, this particular slope has to match the flux with which the or the amount of water vapor that is actually escaping or the amount of liquid that is getting converted to vapor, right. Like for example, in the case of heat transfer what happens, that slope basically gives you how much heat is transferred, right, Q is equal to minus K dt by dx, things like that, right. Here it is basically the mass flux of species A, right. So, this is what actually happens and there is a depression of the concentration gradient, here the concentration is lower, here the concentration is higher, that is because at the interface, right, where evaporation actually happens, right, in that particular region if you consider the mass fraction of A is actually lowered, it has to be lowered, right. So, if you look at this particular evaporation, these things are all interfacial phenomena, it is not happening from here, 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 it is always happening from this zone, right, it is not boiling, right. So, it is only happening across the interface, right. Since it happens across the interface, say initially you had a system, say for example, okay, where everything was kind of homogeneous, right. So, if you sample water from any portion of this mixture, it will always give you that XA value and that XA value is some kind of a fixed value, got it. Okay. So, that is true, that is because the composition is not varying, but however, as soon as you start having evaporation from one of this side, right, from this surface, what happens is that locally the concentration of water vapor will be lowered, right. That is because some water in that zone is actually escaping, some water in that zone is escaping into the vapor form. So, if you look at it in a kind of a discretized fashion, right, evaporation is happening in this zone, right. So, here the concentrations of water vapor will be more or less the same, right, only in this zone it will start to drop, that is because water is getting converted into water vapor locally. Okay. As a result, the other component with whatever that is the other component, that means other species that are present over there, okay, locally the concentration of this particular guy is getting reduced over here. Okay. This is particularly true, for example, if you have water mixed with some other non-volatile solvent, right. If you do that, you will find that the water vapor concentration at the surface will continuously decay. Okay. Similar thing happens in the case of sublimation as well, okay, because there are two species. Okay. Now, so the mass transfer rate is basically limited by both the phases, this and this, how quickly we can supply it and how quickly we can take it away, right. If it is a diffusion driven phenomena, which in most of the cases it is, right, there is no flow as such, right, there is no flow assistance over here. Okay, what you will find is that the water, liquid water gets evaporated into water vapor, that water vapor is basically transported away from the interface, right, by diffusion, because here the slope is in this particular fashion, right. So, locally on the gas phase the concentration of water vapor increases, locally in the liquid phase the concentration of water vapor goes down, right. So, in the liquid what will happen is that more water will rush towards the interface and more vapor will be drawn away from the interface, right. So, this is how evaporation is basically sustained, right. So, when you actually have a saucer of water, okay, let us consider this example. So, when you actually have a saucer full of water, actually let us go to the journal. Let us look at this, that you have a saucer full of water, right. So, this is liquid water and say you have mixed it with something, right. So, it is basically water plus some non-volatile solvent. Non-volatile solvent means it vaporizes very slowly, right, that is what we mean. This is the interface, this is air, okay, hanging over there. Now, what happens, what is the mechanism of evaporation in this case, right. So, that is what we want to answer, correct. Okay. So, what happens is that locally some liquid water vaporizes, right, from the surface, it does not happen from here, it happens only from the surface layer, correct, and it creates an enhanced concentration of vapor on the liquid side. So, that is the vapor side, right. Okay. So, on the vapor side, so if I have to plot this on the vapor side, if I just look at this particular distance, okay, there the concentration of water vapor increases, okay, in the vapor side, right, whereas on the liquid side the concentration of water vapor actually decreases, right, all happening in this small layer, okay. Okay. So, now if this water vapor is saturated completely, I mean this water vapor is present all over, right, okay, the evaporation should actually stop, correct. Okay. This has happened, this is the mechanism, this is because air in this particular location, right, just above the interface, if this is the interface, just above the interface, if you consider that air layer. So, this is air plus water vapor, right, that is coming, and this water vapor source is basically the interface, right. Now, air you know has got some particular saturation pressure, right, water vapor has got a particular saturation pressure. In other words, if the relative humidity of this particular section, this RH becomes equal to 100%, right, then what will happen is that no more water vapor this air can actually accommodate, right, because it cannot hold anything more, it is already at its full capacity, right. The evaporation from this surface will stop. Okay. This is what happens when you actually have a very humid environment, right, very humid, like for example, if you want to dry your cloth, say for example in a very humid environment, say during the monsoon, okay, not because of the monsoon per se, but say there is no rain, but the atmosphere is very humid, right. So, 90-95% humidity, okay. So, that means the air in this particular region takes a little bit of water and becomes saturated, right. So, what is the mechanism for relieving this, correct. So, the mechanism of relieving this is, if you, this is the layer which is very close to the interface, right. If you look at a layer which is very away from the interface, okay, far away from the interface, right, here what will happen is that here the water vapor concentration is low, okay, if it is during the winter season what it is right now, right. So, in this near the interface the concentration is high, away from the interface the concentration is low, particularly it is say Bangalore's weather, it is like 40-50% relative humidity, right. So, water vapor by natural diffusion will go from here to here, right, that has to happen, right, because it has to flow from a high concentration to a low concentration, that is exactly what it does. So, as soon as it does, this region now gets relieved, okay, it gets relieved, right. So, as soon as this region gets relieved, okay, more water can come now from the liquid side. Got it. So, this is the mechanism of evaporation, right. So, here what will happen if we draw it across the interface, okay, here the concentration of water vapor will be high, away the concentration of water vapor will be low, right. So, it is from high to low, right, whereas on this side of the interface, right, on the liquid side. So, this is the air side, right, this is the liquid side, right. In the liquid side of the interface what will happen? It will be just show the opposite trend, right. So, this is actually low, this is actually high, right, because here the liquid is locally depleted, right. Okay. So, this supplies liquid to the interface, this takes away water vapor from the interface, right. So long this process continues, your evaporation continues, you got it. This transfers liquid towards the interface for it to evaporate, this takes the vapor phase away from the interface. So, that this region, if we call this as a region, right, these two regions can be relaxed, got it. Okay. So, that is exactly what we have done over here. Okay. So, one other thing is that the gradient of species in, let us go back to the, so the gradient of species A in the solid is greater than the gradient in liquids and greater than the gradient in gas. This you will always observe. That is because these are governed by the relative mass diffusivities. Okay. So, because the mass diffusivity in one case is lower than the other and the gas phase mass diffusivity is the highest usually. So, the gradient will be the lowest, right, because it has to match the flux, right. For matching the flux there are two things, one is basically the diffusion, the other is basically what we call concentration gradient, right. So, if the diffusion is low then this has to be high, okay, to match the flux, okay. And usually the gas mixture is approximated by an ideal gas, okay, and things like that. These are very standard notations, okay. Now, the other question that you might want to ask, that see we already saw that with curvature, okay, there was a depression of the vapor pressure, right, of the saturation pressure, that we did in the last class or the last lecture. Okay. Now, here the question that one would like to ask is basically, when you have this liquid to gas or solid to gas kind of transitions, right, the partial pressure of water vapor in the gas mixture at the interface, okay, is usually given by something called the Rao's law. Okay. This is called Rao's law. Okay. So, this is basically, if you look at these two terms over there, this P A at y 0 minus and P A at y 0 minus, these two are basically the partial pressure of A in the gas mixture. It is the partial pressure of A in the gas mixture just adjacent to the interface. That is why you have written that minus, right. It is just on the other side of the interface, got it, just on the other side of the interface. And this XAL and XAS, whatever you call it, is basically the mole fraction of species A in the liquid, or it can be the solid depending on which way you are looking at. Okay. And P saturation that you see over here is basically nothing but the saturation pressure at the interface or close to the for which the temperature of the interface is given. Okay. So, if the interface temperature is Ts, you calculate whatever is the P saturation because of that. Okay. Now, if it is pure species, like for example, as I said, pure liquid, okay, or pure solid. Now, in that particular case, this was equal to 1, this we already established in the last thing, right. As soon as we say that this is equal to 1, the partial pressure of water vapor in the vapor phase, okay, is equal to the saturation pressure, right. If it is not, however, which is normally the case with mixtures, the vapor pressure is actually depressed. That is because XAL is always less than 1, right, because it is a mass fraction. The maximum value that it can have is equal to 1, it is always less than 1. Because it is always less than 1, okay, because it is always less than 1, the partial pressure of the vapor phase is actually lowered, okay, when other species are present. That means, when you are dealing with say water plus ethanol, right, mixture, got it. The vapor pressure of water vapor, right, in the gas mixture at the interface, okay, will be lower than the saturation pressure, got it. Okay. It will be lower, it has to be lower. That is because you can think about it like a fight, right. The space is limited, right. So, there is an interface, right. Here you have two species like species A, XA and say XB, correct. Both are trying to evaporate and go into that same space, right. The space is limited, right. Okay. So, as it tries to go into the same space, obviously if it is alone, okay, its pressure will be the same as its saturation pressure. Since it is not alone, right, depending on what amount of A and what amount of B is present, okay, its pressure that is present in this particular region is consequently lowered. It is basically common sense, right. Pressure is what? The number of molecules you can consider in a particular space, right. So, species A, okay, is actually evaporating into the same space, species B is also evaporating into the same space, right. So, they are both fighting basically for the same space, right. Since they are both fighting for the same space, right, it is obvious that the pressure of species A in that space will be lower than the saturation pressure that species A would have had if it was present alone, right. So, if it is just a pure liquid water droplet, that space will be only water vapor, right, H2O. Now that it has got ethanol, okay, this space will contain water plus ethanol, right. It will have the vapor phase of both. As a result of that, you cannot have the same partial pressure, right. So, the mass fraction of species A in the gas phase now can be determined just by that partial pressure that you have determined over here divided by the total pressure. Total pressure is always the same, okay, because it is a total pressure, it is atmospheric, right. Okay. Similarly, you can find out other things like mole fraction and things like that. Basically, you bring in the molecular weight because species A and species B are there. Okay. So, conceptually it should be clear that why evaporation happens, this is what we explained, okay, and how it actually proceeds, right. There is a depression of vapor pressure if we are dealing with two species. If we are not dealing with two species, there is no curvature effect, right. We will have the partial pressure of species A to be the same as the saturation pressure, okay. So, that part needs to be very clear, okay. So, here we have tried to explain how evaporation happens across the interface, okay. So, in the next class we are going to look at a particular topic which is basically what we call the droplet, okay, and the droplet is what we are going to do in the next lecture.